the learning outcomes first. So in this topic, you have to learn about how does current is induced from magnetic field. So the current that induced by magnetic field is what we call as induced EMF. This one is in voltage. So through this induced EMF, there will be current that flow in the circuit. Even though there is no power supply, but there is current. This one sounds interesting, right? Because this is somehow a free electricity. So after learning this topic, you know how to generate your own electricity without have to pay the bills. Okay, and before we learn into the induced current or induced EMF, there is one new term that you have to know, which is called as magnetic flux. So you have to know how to calculate magnetic flux and how would you get the so-called free electricity. So the one and only one concept in this topic, Faraday's law, okay, and cope with Lenz law. Lenz law, I think is the Lenz law is the partner of Faraday's. Okay, even though they born at different time, but both of their concept of both of their theory, they can combine together and give you the magnitude and directions of your induced EMF. Then following will be the application of this induced EMF. Okay, the first one is electric generators, the one that used in the power plant and how we actually get our electricity at home. All right. Motional EMF, another types of the application. So motional EMF is something that you can look into. So from there, you can also generate your own electricity. Inductance. Another word for inductance is actually solenoid. Okay, so if you know how to make solenoid, you can also generate your own electricity. Finally, transformer, right? So the history of how does scientists discover about free electricity. So we have learned in previous topic that if there is current, then there is magnetic field, right? From previous topic 9, when there is current, when current flows into this wire, all right, there will be magnetic field generated, okay? So magnetic field, let's say, generated like this, okay? When there is current, there is magnetic field. So that's why Faraday's, okay, think of about, since I can get magnetic field from current, then I could also get current from magnetic field, right? So this is what always a physicist will think. They will always think like, if I can get this from A to B, then somehow there is a way to connect B to A, right? So he's trying his experiment in order to get the current from magnetic field. However, right, his hypothesis doesn't work, okay? When there is magnetic field, there is not always that you will get current. However, he discovered something new, okay? He found that changing current in coil X here, okay, the word is the change here. Changing current in coil X here will, however, result in the current generated in your coil Y. So meaning that when there is a change in current, it will result in the change in magnetic field. And eventually, this is how the induced current is being produced. So that's why this has become the directions of the research of the scientists. And in fact, this is also our one and only one concept in this topic. So before we move into the main concept, now we have to look at the new terms first, okay? There is one term here called as magnetic flux. So magnetic flux is given by BA cos theta, with B is the magnetic field, A is the area of the coil, cos theta and this theta, okay, is different from the theta in your previous topic, is the angle between the normal line and the magnetic field. Okay, so in short, you can draw like this. This is the normal line and this is the magnetic field. So what is actually the normal line? So if this is your coil, then the normal line is this, okay? Which means it is actually 90 degrees relative to the plane of your coil, okay? So let me show you something. Okay, now I would like you to look at here. If let's say this is my coil, okay, so the plane of the coil is this. So where is the normal line? The normal line is this, right? Because it's coming out from the plane. This is the normal line to my coil. Huh? Normal line to my coil is like this. Can see? All right. So means it is actually 90 degrees relative to the plane of this coil. Okay, so that is normal line. So magnetic flux, in another words, it can be called as here, the total number of magnetic field lines passing through the area enclosed by the loop. Okay, in short, it is called as a density of magnetic field, the amount of magnetic field that passing through an area. So for example, if you look at here, let's say this is a region with magnetic field. Okay, so when I place a coil here, now this is a 3D illustration. So when I place a coil here, the amount of magnetic field that pass through this area is what we call as magnetic flux. Okay, so magnetic flux is actually equivalent to magnetic field, but it is only limited to a certain area, only limited to the amount of magnetic field in that certain area. Okay, and that area is the area that enclosed by a coil. All right, so in this case, what is the magnetic flux? Okay, so the magnetic flux here will be, okay, the symbol for magnetic flux is called as phi. Phi subscript B. This is what we call this as phi. Okay. Phi subscript B equals to BA cos theta. And B is the magnitude of your magnetic field. A is the area of your coil. Cos theta, and this theta, remember, it must be the angle in between your normal line and magnetic field lines. So now look at this picture. The plane of the coil is these yellow colored things, right? So now from our front view, from the front view here, when we present them in two-dimensional, this is your coil. And the directions of magnetic field is vertical like this. So how do we determine the theta usually? So you have to draw the diagram, okay, with this is your coil. And okay, let's say this is the directions of your magnetic field going downwards. So when you want to start to determine the angle, so what you have to do is start with drawing the normal line. Okay, this is your normal line. Now check on the angle. Normal line and magnetic field, they are 0 degree. So cos 0 is actually equals to 1. So that's why when theta is equal to 0 degree, your magnetic flux is the maximum. All right. Now, what if on your second diagram like this, okay, your coil is like this, but the directions of magnetic field changes its direction like this. So start with drawing the normal line and measure the angle in between your normal line and magnetic field. So that is your angle. Okay, so if you key in the values in your calculator, then you will discover that the larger the values of theta, the smaller the values of your cos theta. Correct? Okay, so this is the second types of magnetic flux. And now let's look at the final one. Okay, so on the last picture here, the magnetic field lines is actually moving horizontally like this. So in this case, if you project them in this front view, so by comparing the normal lines with the magnetic field, you will discover that now your theta is equals to 90 degrees Celsius. So, sorry, not degrees Celsius, 90 degree, okay? So cos 90 equals to 0. So at this point, magnetic flux is equals to 0. Okay, so now I would like you to imagine magnetic flux as something that that you can catch in a container. For example, now magnetic field is water flow, okay? And the coil is your container. So if water flow vertically down like this, and you put your container down here, isn't it you can get the maximum amount of water to enter into your container, right? Another example is like this, okay? The water flow diagonally like this, but you still place your container like this. So at this particular point, the amount of water that you get won't be the maximum, right? Because it is not right to the angle, okay? And another types of example is this, okay? Your water flow horizontally like this, and you place your container here. Do not think about the gravity, do not think about the gravity, yeah, but you just place like this. So imagine that all the water will just bypass your container. It won't go into your container. So that's why there is no magnetic flux. So when it comes to magnetic flux, you have to have a mindset like this. Okay, so that's why in order how to calculate magnetic flux, B, A, cos theta. 3 factors that will affect your magnetic flux. The magnetic field, the area, and also the angle. 3 of them. Okay. Any questions with magnetic flux? Okay, so now let's move on to the example of question. So how do we usually solve the questions that related with calculating magnetic flux? So my advice is to draw a diagram, okay, because diagram helps you to check on the angle especially easily, yeah? So given that the magnetic flux, when the area of the coil is perpendicular to magnetic field strength is 7.5 times 10 to the power of -4. So when it is perpendicular, how does it look like? So you can draw your own diagram. Area of the coil is perpendicular, meaning that now if the area is at the Z dimension and my magnetic field is on to the right, so they are 90 degrees. Okay, when the area and the magnetic field is 90 degrees, and given that the flux is 7.5 times 10 to the power of -4, and the unit for magnetic flux is in Weber, W in capital, B in small capital letter. So find the change in magnitude of the magnetic flux through the coil when the coil rotates. So given that the area of the coil is 5 centimeters square and magnetic field is 1.5. So meaning that the coil is now rotated from the original position to 60 degrees. Now, let's draw the diagram. Green color is magnetic field. And now this is your original position. Rotate 60 degree. So from here to here, this is 60 degree. Now, the new magnetic flux, B A cos theta. So B 1.5, A is 5 centimeter square convert to SI unit times 10 to the power of negative 4. Theta, how do we find theta? So remember, always start with the normal line first. So the theta is angle in between normal lines and your magnetic field lines. So now this is the time when you have to apply your mathematics skills here. Okay, so from here to here, from here to here, 90 degrees. So this one is 30 degrees, right? And from here to here, this is also 90 degrees. So if here is 30 degrees, so your theta will be 60 degrees. Okay, so cos 60. Then you get 3.75 times 10 to the power of negative 4 Weber. Move on to question 2. The original position, and it is now rotated to 90 degrees. So this is your new position of coil X. So what is your magnetic flux? I would like you to try with the method that I used just now. You try it for question 2 and 3. And once you are done, you can type your answer on the chat. Okay, done? What is your answer for number 2? Yes, 0. Very good. So if you write them down, you will discover that, okay, you can write all the values inside first. But what happened here is your B and your A doesn't change. But what is changing now is because of your theta. So if you look at here, the plan is like this. This is your plan, like this. Then the normal line is here. This is your normal line, correct? So what is the angle in between normal line and your magnetic field line? It is just at 90 degrees. So 90°. Oh. So cos 90 equals to 0. So at the end, you won't get any magnetic flux. Huh? How about number 3? What is your answer? Number 3? When it's rotated for 180 degrees. Negative 7.5. It is, so when you rotate that 180, isn't it just back to its original position? So if it is back to its original position, it is the original values of flux. Okay, 7.5 times 10 to the power of -4, right? Okay, so once you have get your magnetic flux, you know how to find magnetic flux. Now we go into our main course, main dish of today, Faraday's law. So what does Faraday say? Faraday says that the induced EMF, okay, the so-called free electricity, the amount of free electricity that you generated is actually proportional to the rate of change in magnetic flux. Okay, so that's why we have to learn about magnetic flux. Okay, so it's about the rate of change in magnetic flux. Have you learned in chemistry the reaction rate? Reaction rate is something like d over dt, right? Let's say the rate of change of the concentration of the certain chemical, okay, d over dt. So same goes with the rate of change in the magnetic flux. It has to be something delta, okay, delta can serve as d also, yeah, d over dt of this magnetic flux, okay. So write them down as a formula. Epsilon stands for induced EMF equals to negative n is number of turn times the change in magnetic flux over change in time. All right, so that is Faraday's law. The amount of induced EMF is directly proportional to the rate of change. The keyword is the change of magnetic flux. So this negative sign here is contributed by Lenz's law. So negative here only shows the direction. Faraday's contribute the magnitude of the induced EMF. Lenz contribute on the direction of the induced EMF. Oh, no direction again. Okay, so what does Lenz's law say? It says that the current that produced by an induced EMF move in a direction so that its magnetic field opposes the original change in flux. Okay, sounds very, very deep, right? Okay, so now, because of the change in the flux originally at first, due to the change in flux, right here, due to the original change in flux, the coil will induce an induced EMF. So from our topic 9, we know that when there is current, there is magnetic field. So same goes with this induced EMF, okay? This induced current, okay? So when a change in magnetic flux result in an induced EMF, this induced EMF at the same time will produce the magnetic field as well, right? So I call this as induced magnetic field. So this induced magnetic field will oppose the original change in flux. So this is how the directions of the induced EMF is determined, because it is following the laws of conservation of energy. When something is changed on your left-hand side, your right-hand side will do something in order to oppose the change. So this is what happened in this Lenz law, and in also and is applicable to this induced EMF. All right. Any question? That is the most difficult parts that claimed by your senior. So if you think, it's not difficult, congratulations, you are better than your seniors. Okay. So if you have no question, then I shall move on to explain again. Okay. So Lenz law tells about the direction. So from Faraday's, we know that there will be induced current when there is change in magnetic flux. All right. So meaning that change in magnetic flux here will at first induce a current, right? So the directions of this induced current will move in a way that so that its induced magnetic field here will oppose the initial change in flux. So this is what is being mentioned by this Lenz law. This is your induced current. This magnetic field is actually the induced magnetic field. And this is the change in flux. 10. Okay, I repeat. From Faraday's law, there is, when there is a change in the magnetic flux, there will be induced current. All right, but we don't know how will the current move, right? What is the directions of the current? So how to determine the directions of current? Okay, it actually aims to follow the conservation of energy. Yeah, so the current will move in a direction so that its induced magnetic field, this induced magnetic field is caused by this induced current. Remember, this is topic 9. Topic 9 says when there is current, there is magnetic field. So the current will move in a direction so that this induced magnetic field will tend to oppose the original change in flux. So this is how they are actually related. How does the directions of the induced current oppose change in flux? So I will show you later, yeah? So that's why I say the keywords here is the change. When there is a change in magnetic flux, meaning that the magnetic flux increase or decreases, which is the direction of the magnetic flux? So there is a change. So when you want to oppose the change, your induced current will do something so that the induced magnetic field will try to oppose the change. All right. So now let's look at the example first. This is the calculation. Okay, now let's look at this first. How do we actually determine the direction of the induced current? So in this experiment, what happened is there is a coil. This is your coil, okay? And the magnetic bar is being dragged near to the coil with north pole approaching the coil. So what happened is when you drag the coil, let's say from this position to this position, what happened to the magnetic flux inside here? This is the magnetic flux that you would like to study. What happened? Okay, the change in the flux here is there is an increase of the magnetic flux, right? At first it is so far away, and finally it is so near. So meaning that the amount of magnetic field increases that cause an increase in your magnetic flux. So there is an increase of the magnetic flux. Now we have to think about the direction as well. So what is the direction of the magnetic flux? There is an increase of the magnetic field, which is the directions of the magnetic field is going upwards. Correct? So when there is a change in magnetic flux, there will be an induced current. So how do we determine the directions of induced current? Now, step 2, oppose the change. So according to Lenz, it says that the directions of induced current produced will aims to oppose this initial change in flux. So in order to oppose this one, the system will like to decrease the amount of magnetic field which is going upwards. So in order to decrease this one, I will have to produce magnetic field in the opposite direction, which is going downwards. Yeah. So from this one, the directions of induced current, according to your right-hand grid rule, will be clockwise from the top view. Okay. So now I'm putting this into the triangle just now, the triangle relationship just now. Yeah. Remember from our Lenz law, it says that when there is a change in the magnetic flux, there will be induced current. So according to topic 9, when there is an induced current, there is definitely an induced magnetic field. So Lenz says that this induced magnetic field will move in a direction so that it will oppose the original change in flux. Okay, so now I would like you to look at this example. When your magnet is being dragged upwards, the directions of induced current inside the coil is moving clockwise from the top view. Okay, moving clockwise from the top view like this. All right, so when the magnet is dragged towards the coil, there is a change in magnetic flux inside the coil. So this causes an induced current to be produced in the directions of moving clockwise from the top view. So the current that moving clockwise from the top view will produce a magnetic field with your right-hand grid rule, which is going downwards, correct? So this magnetic field which is going downwards is actually aims to oppose the original change in flux, because the original change in flux, when you drag the magnet bar near to the coil, the change in this magnetic flux is actually an increase of the magnetic field which is moving upwards. So that's why the direction of this induced current is produced in a way so that its induced magnetic field aims to oppose the original change in flux. Okay, I give you 2 minutes to digest. Okay. So we will look into more example later. Now let's do some calculation for Faraday's law first. Yeah. Okay, the plan is 12 centimeter in diameter. So this is diameter. So what is your radius? 6 centimeter. Your wire, okay, or your plan of your coil is initially parallel. So this is your initial position, parallel to the magnetic field. The strength of magnetic field is 1.5. So the loop is rotated so that its plane is perpendicular to the field. So rotated, now it is perpendicular in 0.2 seconds. So that is your time, change in time. What is the average induced EMF in the loop? So we would like to find the induced EMF. According to Faraday's, induced EMF is given by negative N times the change in the flux over change in time. Number of turns, if it is not given, so by default it will be equals to 1. All right, so let's expand the equation. Magnetic flux, write down the full equation of magnetic flux, BA cos theta over time. So usually how do we simplify the equation? We will just move out the constant, the values that is not changing. So in this case, the factor that change here is actually your angle. So what we do is move out the not related one outside and remain change in cos theta over change in time. So since number of turn is not given, so by default we put it as 1. Magnetic field 1.5, area pi r square. So r 0.06. Convert to SI unit. Now change. Always remember, it is always the final value minus the initial. So for change, it must always be final minus initial. So now let's check on our theta. At the initial position, this is your normal line. So theta is 0 degree relative to the wait, hold on. Initially, it is parallel to the magnetic field. Oh, sorry. Yeah, this is your normal line. Correct. Yeah, this is your normal line. So the angle between your normal line and your magnetic field, now magnetic field is horizontally like this, I'm moving to the right. So your angle is 90 degrees. Now, when it is rotated to perpendicular to your magnetic field lines, so this is your normal line. Normal line and magnetic field, at the final position, it is equals to 0 degrees. So when you put into your values here, it will become cos 0 minus cos 90 over the change in time, which is 0.2 seconds. So you get 0.085 volts for your induced EMF. So since negative only shows the direction, so in your final answer, you can actually remove the negative. So we will determine the directions with Lenz's law letter. Okay? So that is about the calculation. All right, so back to our Lenz's law. In order to determine the directions of magnetic field, okay, so that's why we have developed the 3 steps for you. Just follow the 3 steps and you will get your direction. So the 3 steps here are, the first one, observe the change. So put in a symbol as delta phi b. Okay, delta, this triangle means delta, means change. Okay, so observe what is the change in the magnetic flux. What is the direction? Increase or decrease? Okay, whether the change refers to either increase or decrease. And secondly, once you have identified the change, now according to the change, we would like to oppose. So if in your first step it is an increase, then on your second step it will be a decrease. So I would like to decrease something. So based on your decision, if I would like to decrease something, so what should you produce? Then from what you would like to produce, from there, by using right-hand grip rule, to determine the directions of induced current. Okay, so now let's look at another example here. So when the magnet bar is being dragged away, now the directions of the magnet bar is moving downwards, which means from initially there is a lot of magnetic field across the coil. When it is moving downward, the amount of magnetic field that across the coil will be decreased. So that's why your initial change in flux that you observe here is actually a decrease in the magnetic field, which is moving upwards. So according to Lenz, in order to oppose the change, the system would like to increase. Increase what? Copy the same things down here. Magnetic field, which is moving upwards. So according to your conclusion here, what should you produce? I should produce more magnetic field, which is moving upwards in order to achieve this. So by using right-hand grip rule now, the directions of induced current will be anti-clockwise from the top view. Okay, so there are more exercises that you can do it and check your answer from the pre-lecture video. All right, but what I want you to do is remember the 3 steps. So whenever you encountering the questions that related with the directions of magnetic, directions of induced current, please use these 3 steps in order to help you to determine the directions of induced current. Okay, so let's have a break of 5 minutes while perhaps you can try these 2 questions. Okay, before we move on to the application. So come back at 10:25. Okay, welcome back. Right, so now let's move on to our first application, which is a moving conductor. All right, so moving conductor, it consists of metal bar. You have a metal bar like this. Okay, you have a metal bar like this, and you place a moving rod here. So this rod can move to the left or to the right. So when you move the rod, what happens is the area of the coil will change, right? So let's say if the rod is now moving to the right like this, initial position and final position, yeah? So this is the initial position and this is final position. So what happens is, this is the initial area, isn't it? So when it is being dragged to the right, now there is an increase of the area. So the factor of change here, the changing factor is actually due to the change in area. So the formula can be derived from initially the Faraday's law. Okay, if you look at here, it's due to the change in area. So area is given by L, which stands for the length of the rod, this one, times the amount of displacement. That is your change in area. Okay, so from there, when you further derive, you will get this. So you won't be asked how to derive the equation, but you have to know which formula to be used. So for a moving conductor or moving rod like this, you have to use NBLV cos theta. B stands for magnetic field. L refers to the length of the conductor, which is here. V is the velocity of the movement. How fast does it move? Okay. So now to determine the direction, again by using the 3 steps for Land's law. The first step is to observe the change. So if you look at here, this diagram, when the rod is being dragged outside, what is the change? There is definitely an increase of the magnetic flux. So what is the direction? If you look at here, the part highlighted with the yellow color is the initial area. Then when it is being dragged outside, this is your new area. So what is the change of the flux? There is an increase of the cross product, right? So if you count the amount of the cross product inside initially and the final one, the amount of the cross product in the coil is increased. So there is an increase of the cross product. So according to Lenz, the system would like to oppose the change. To oppose the change, if the change is an increase, then to oppose, there has to be a decrease. Decrease what? Decrease the cross product. So in order to decrease the cross product, you have to produce dot product. So using your right hand grip rule, the directions of induced EMF to produce dot product, your thumb is now pointing out from the screen. So the directions of the induced EMF will have to move anti-clockwise like this, isn't it? So moving anti-clockwise. So it actually in line if you have learned about Fleming's right hand rules in your high school. So remember, for your right hand, This is your direction. This is magnetic field, and that is the motion. If you remember, yeah, thumb shows to the right. Magnetic, if this is right hand, thumb shows to the right, magnetic field going into the screen. So your current is actually moving upwards, which shows the current moving upwards here. However, I do not encourage you to use Fleming's right-hand rules because it's only applicable to certain scenario, not apply to all types of the application, especially when it comes to the inductor letter. All right, so that's why we are teaching you this Lenz's law in your syllabus, in your foundation. It doesn't actually tells you how to use the Fleming's right-hand rules anymore, okay? But then they want you to learn about Lenz's law. So that's why I do not encourage you to stick with what you have learned in high school with Fleming's right-hand rules. But you can still use it to double check your answer. But it's only applicable to moving conductor and some part of generator. All right? Now let's look at the example. Magnetic field strength is 0.15. The length of the wire, the wire is 40 millimeter. Okay, so this length of wire must be the length of the wire that enclosed by the loop. So only here, not the whole wire itself. So if the wire move at the velocity of 1.2 meter per second, find the induced EMF and also direction. Okay, now firstly, determine the magnitude. Since this is a moving conductor, so the formula that we use is NBLB cos theta. So this theta again, it is still the angle in between normal line and magnetic field. Okay, so the angle here will be equals to 0 degree, right? Magnetic field is coming out from the page, normal line, it is also at the Z dimension. So 0 degree. Since number of turns is not given, so by default is equals to 1. And usually for moving conductor is only 1 turn because only 1 round. Okay, so magnetic field 0.15, length 40 millimeter times 10 to the power of -3, velocity 1.2. This is also equals to 1. So 7.2 times 10 to the power of -3. Unit for EMF is in voltage. So since negative only shows the direction, you can actually ignore the negative sign. All right. Next, move on to determine the direction. Remember, to determine the directions, you need the 3 steps. The first one, observe the change. Second one, according to Lenz, in order to oppose the change. The third one, by using your right hand grip rule to determine the induced current. Now, look at your diagram. Yeah? The wire is being dragged outside, let's say dragged up to here. So this is the initial area. And this is the final area. So what are the change? There is an increase of the dot product. So in order to oppose the change according to Lenz, I would like to decrease the dot product. So to achieve this, to achieve a decrease in the dot product, so the system would have to produce cross product. Then finally, from my conclusion, use right hand grid rule. To produce cross product, I would have to produce a directions of the current moving in clockwise direction. So when passing through this rod, it has to be moved from P to Q. Okay, P is this point, Q is here. So the direction of current is going down like this. Okay. The second application is generator. So generator, the magnetic field doesn't change. Your area doesn't change as well. So the factor of change here is your angle, the theta, because it is keep on rotating in the region of magnetic field. So simplify your equation and take out theta. And theta, in terms of writing a functional equation, is always given as omega t. Remember your simple harmonic motion? Right. Instead of theta, when it is being presented in terms of a function of time, theta is equals to omega t. Okay. The SI unit for theta, okay, is not degree, it's in radian, right? So remember omega is radian per second. The unit for time is seconds. So when you multiply radians per second with second, it is equals to radian as well. Okay, so it's written as omega t. Now, differentiation, okay, of this one will give you negative omega sine omega t. Okay, and this is your final equation for a generator. Again, it won't be asked how to derive, but you have to know how to use this equation when it comes to generator. Okay, N stands for number of turns as usual. B is your magnetic field. A is the area of your coil. And omega, angular velocity, means how fast does this generator rotating. All right, sine omega t. Okay, omega t is your angle. Okay, so due to this continuous change in the angle, this is how we will get our directions of current in a sinusoidal form like this. If based on this equation, you will get a sine graph, which is like this. And how to determine the directions? There is one question in your advanced practice problem, which is dealing with the direction. You can check on that question in your advanced practice problem. Okay, if you haven't go through any question in your advanced practice problem, remember it is under item 2 of each of the topics. Okay, there is a lot of questions and some of them are quite challenging. You can actually go and look at them. All right. The third one would be inductor. Inductor, in another word, it is also a solenoid. So this inductor effect is actually a self-induced electrical component. Why we call this as self-induced? Because of the orientation of the wire itself. Okay, the solenoid. This is a region in the middle of your solenoid. There is a region where there is a possibility of getting a change in magnetic flux due to this region itself. So how will it experience the change in flux? So whenever it is being placed in a circuit, when there is a change in the current, that flows through your solenoid, remember, there is a change in the magnetic field. This one is from the power supplier. So let's put PS as power supply. When there is a change of the current from the power supply, the red color one, there will always be a change in the magnetic field. Okay, this one is due to the current of the power supply. So when there is a change in the magnetic field, what will happen? There is a change in magnetic flux. Because the amount of magnetic field that passed through the center of the solenoid is now changing due to the change in the magnetic field. So when there is a change in magnetic field here, what will happen? according to Faraday's law, there will be an induced current. Okay, so that's why in your derivation from Faraday's law, the factor of change here is actually the magnetic field. And remember, magnetic field, there is a change in magnetic field. It is because of your current. Okay, and since this is a solenoid, that's why your formula for magnetic field will be the formula for the solenoid. Remember, mu naught Ni divided by the length of the solenoid. Okay, so this is how we derive our equation. And at the same time, the induced current of the inductor is also given as this. Change in current over time times the inductance. So when we combine these two together, we will get our final equation for inductance. Okay, inductance is referring to the strength of solenoid. Only applicable to this electromagnetic induction. Okay, so how to derive to get inductance? Okay, is in your syllabus, which means you have to know how to derive. And we will go through this one in our tutorial workshop later also. Okay, so the directions of the induced current in your inductor. So you have to also using the 3 steps here, observe the change first. So what happened is, now look at this circuit. It is when the switch is just closed. Okay, initially the switch is open, no electricity. Okay, so there is no current. So when no current flow through your solenoid, no magnetic field. Means magnetic flux is also equals to 0. Right. The next moment when the switch is just closed, immediately there will be current flowing through your solenoid. So what happened is, from no magnetic flux, then there is a maximum magnetic flux flow through your solenoid, from no magnetic flux to maximum magnetic flux. So isn't it there is a change in the magnetic flux? Yes. Okay, so what is the direction? The change in the magnetic flux by using your right-hand grip rule, yeah? The solenoid right-hand grip rule, the directions of magnetic field generated by this current from the power supply is going downwards. So there is an increase of the magnetic field which is going downwards. Now, to oppose the change, then the system would like to decrease magnetic field which is going downwards. So I have to produce magnetic field which is going upwards. According to right-hand grip rule, in order to produce magnetic field which is going upwards, magnetic field which is going upwards, then it will be anti-clockwise from the top view. Your eye is here, anti-clockwise from the top view. So if I have to label in the diagram, I use green color to represent the induced current anti-clockwise from the top view. Then it will be coming out from your solenoid. This is your directions of induced current, which is actually opposing your power supply. Okay, so that's why if you notice in a normal circuit, okay, usually a normal circuit that is without inductor, like this picture, the moment when you turn on your switch, you will see that the current will jump up immediately to the values from the power supply, like the light, like the LED light at your house. The moment when you turn on the switch, the light bulb immediately goes to its full brightness. Why? Because the current is actually shooting upwards immediately at the moment when the switch is just closed. However, in a more complicated circuit which contains inductor or solenoid, you will discover that the current will slowly increase. After a certain time, then only it will reach its full brightness. So this example is somehow like the monitor of your computer screen. When the moment when you turn on the screen, it actually won't come out to its full brightness immediately. However, it took some time to slowly, then it go brighter and brighter. Okay, why? Because of the purpose of the, because of the inductor that doing something inside. If you still remember just now, yeah? Due to the directions of induced current, which is opposing the power supply, so your net current this is due to the induced current, which is moving in the opposite direction. Okay, so the net current will be small at first because at initially the change is the maximum. So when your power supply is continue to supply to the whole circuit, the change in the magnetic flux will become smaller and smaller. That's why your induced current will become smaller as well. So that's why the net current will become larger and larger. So finally, when there is no more change in flux, then that is the time when you will get the maximum current from the power supply. All right. So when something that can generate current by its own, we call that there is an energy that contained in the solenoid itself. So the energy contained in the solenoid or inductor is given by half Li squared. Just like remember your energy in your capacitor, half CV squared. Okay, so that is the capacitor itself. Then for inductor, this is the inductance itself. The unit for inductance is given by H, stands for Henrys, yeah? So capital letter H, I is the current, all right? So what will happen when it is now open the switch, okay? With the current when there is current from the power supply. So at this time, your magnetic flux is the maximum. The next moment, you turn off the current. And suddenly magnetic flux equals to 0. What will happen to the induced current? Again, observing the change. Okay, when current of power supply flow like this, there is a magnetic field which is moving downwards, right? So when there is no current from the power supply, there is no magnetic field. So what is the change here? There is a decrease of the magnetic field which is moving downwards. So according to Lenz, you would like to oppose. So to oppose this one, I would want to increase magnetic field which is moving downwards. So I will want to produce magnetic field which is moving downwards as well. So in order to get magnetic field which is moving downwards by using right hand grip rule, your directions of current will be clockwise on the top view. So direction of the induced current to be clockwise from the top view will be like this, coming out from the solenoid. Isn't it just the same as the directions from the power supply? So that's why the current when a circuit without a conductor, the moment when you switch off or you open the switch, when you turn off the switch or you open the switch, your current will just straight away goes to zero. However, for a circuit with a conductor, instead of it straight away goes to zero, remember, due to this induced current, it will slowly goes down to zero. Okay, so this part is due to the induced current. So that also explains why when there is a certain electricity cut off, the light will turn off first before your monitor screen. It will take some time before it is totally shut down or it is totally off. Why? Because of this inductor. All right, so now you can explain to your friend. It is not because of the magic. It is not because of what else? Oh, but it's because of the inductor. All right, so now let's look at Iron Man. So if anyone watched this before, am I in the same generation as you? Okay, this is one of my favorites movie. Okay, yeah, I'm not too old also. Okay, now, so if you watch Iron Man 1, when Tony Stark was being kidnapped in order to do some weapon for the terrorists, he actually did something, he do something secretly in order to make his Iron Man suit. So in his conversation with another doctor, he is mentioning that if his math is correct, the total energy that generated with the arc reactor will be 3 gigajoule per second. All right, so we have searched online and found his blueprints for his arc reactor. And we assume that inside his arc reactor, there are 10 inductors inside, which means inductor inside. And from the diagram or from the design, okay, the dimension of this arc reactor is given by this, okay? And we assume that the number of turns is 500 turns. So what is the amount of current that is actually needs to be generated in order to produce 3 gigajoules per second? Okay, so from our information that we have, okay, so let's write down here. The energy is 3 gigajoule per second, and there are 10 inductor. Number of turn assumed to be 5,000, and the dimension is 3. The diameter is 3.5 millimeter, and the length is 7 millimeter. All right, so since we have the information for the solenoid, let's find the inductance first. Inductance mu naught n square times area divided by length. Number of turns 5,000. Area pi r square. So r is 1.75 millimeter. So 0. Length of the solenoid is 7 times 10 to the power of -3. And we get 0.0432 Henry. Now, from the energy equals to half Li squared. This is the total energy. So 10 inductor times 10. Giga, 3 times 10 to the power of 9 joule per second. So half I squared times 10. Find the values of your I. (1.18 times 10 to the power of 5 ampere per second. So the amount of the current that produced by this arc reactor is 1.18 times 10 to the power of 5 ampere per second, which is crazily huge. So that's why this Iron Man should still not that realistic in life. Why? Because if you get such huge current, the whole suit will definitely melted. You know that 1 ampere of the current can kill an elephant. Huh? So can't imagine a normal person that can take this amount of current. So that's why it is still in a sci-fi in movie. So that's why if you notice, he actually has to look for something in order to cool down his arc reactor. Huh? So perhaps sometimes in the future, you or someone else, you might get to invent the arc reactor, and hopefully before I die, I can see your invention. All right, so that is about inductor. So the last part about transformer, I will cover later together with the tutorial workshop later. Any question? So you can take the remaining time in order to research or to digest, especially the Lenz law, if you still find it very difficult to understand. And later on during the tutorial workshop, we will have more exercises on Lenz law also. Okay, so yes. And I hope it's actually from one of our students. Okay, we have actually been introducing this idea to the students for the past few semesters. Some of them graduated already, so I'm this old, but some of them still studying. So that's why we are introducing you to, you are our future engineer. So we would like to introduce this idea to you so that it will open your mind in order to look for more possibilities to come up with something which will make our life easier. Okay, this is what engineers do, right? So that's all for now. I shall see you later at 2:30 for the tutorial workshop. Bye bye. Thank you and bye bye.